Well, how are you guys doing? My mouth is like 90% better. So, it's good. Yeah. I could speak, it just hurt a lot. So my tongue was swollen. I had a bad canker sore on the side of my tongue, and every time I'd say something, the canker sore would rub against my teeth, and it just made it hurt really bad. And the more I talked, the more swollen my tongue would get, and then it would just get worse. I had a canker sore on my tongue, and my tongue was swollen because it was kind of infected, and so every time I tried to speak, the canker sore would rub against my teeth, and it would hurt really bad. There was one other time about 8 or 9 years ago where the similar thing happened, where I had to teach without talking. That lesson went better than Monday's lesson. Was it? Yeah. What I would have changed differently on Monday was I should have. I had you guys find the eigenvalues and I gave you guys the eigenvalues, but I had you guys find the eigenvectors. And that was a nice review for the exam coming up, but we didn't really need to have you guys find that. And so it took time and we didn't get finished the thing. So but that didn't have to do with me being able to speak or not. That was just a poor choice before class. So, yeah, but yeah, could have been worse. Could have been worse. So. Yeah, I took a sign language class when I was actually a grad student. Took the first sign language class here. It was kind of cool. It turned out really nice. I can fingerspell pretty well. I've forgotten a lot of it, but a couple of my kids are learning sign language. But where it came in really handy was in church, when my wife and I would be at other ends of the of the pew, and with all the kids behind, and we'd like sign or spell to each other. And I'm like, who's that? Who's like, this is for who, right? And you're like, who's talking? So, yeah. So it was like really nice to be able to do some sign language. So, yeah. Even now, sometimes, if kids are around, the younger kids, the ones that don't know sign language, like or even if they're around, I'll like spell something to my wife. Something you don't want to say. All right, let's get started. Who'd like to pray for us? Anyone want to pray in sign language? Anyone know sign language that they want to pray? Okay.
I can pray.
It's one of the nice, you do get to keep your eyes open if someone's praying in sign language, so you can watch the prayer. So, yeah. Okay, crazy story. I was in general conference. I went with my wife. My wife's family had tickets, so I went with my wife to general conference. I think it was Sunday morning. This was before the conference center was built. So it was in the tabernacle, and we had pretty good seats. And I was right on the aisle, and down at the end of each of the aisles was a security guy. So they're saying the prayer, and during the prayer, I'm like, I wonder if the security guys close their eyes during the prayer. So I peek up and I look, and the guy's looking right at me. And I'm like, but he didn't, yeah, they don't close their eyes. They're not stupid. Like, if they close their eyes during the prayer, like that would be the perfect time to do something, right? But yeah. There's more to that story too, but we don't have time right now. Let's get started. Yeah, who wants to offer a prayer for us?
I can pray.
Thank you, Braden.
Our Father in heaven, we come before you this day to give thanks for our many blessings, for our opportunity to be here with Brother Corey and to learn out linear algebra. Father, please bless him that he'll be able to be a good help and be able to teach us well today. Bless us that we'll be able to do well in the midterm and remember these things, apply them for the rest of our lives, and use these tools effectively. We get these things in the name of Jesus Christ.
Amen. Thank you. Exam 2 starts tomorrow. it goes up through 4.4, so up through similar matrices. There's lots of review tests online, some good review sheets. Study those. If you have questions, you can get on office hours, and I'm happy to go over the problems from practice exams with you. So Monday's a late day. Don't talk about the exam after you've taken it. Okay. Good rule of thumb: only you can say how long it took you, and that's it. So, okay. Just to recap some things on similar matrices that we didn't get to talk about yesterday or Monday. Ha ha ha. Okay. So similar matrices, one way to think about the similar matrices is that they do the same transformations, except not in terms of x's and y's, like not reflecting along the line y equals x and stretching in the x direction, but in terms of eigenvectors. So they'll stretch the same amount in their eigenvectors. So every matrix that stretches one eigenvector twice and another eigenvector 4 times, they are all similar matrices. Okay, so they're all connected. And they have really nice, you can show that they have nice properties, like that the determinants have to be the same, the eigenvalues are all the same. If one's invertible, the other one's invertible, all that stuff, a whole bunch of stuff. Well, what's really nice though is when you can show that one matrix is diagonal, is similar to a diagonal matrix, because then you can get this factoring, and this factoring can help us with simplify a whole bunch of things that are computationally complex, like taking powers, which is what we have you guys practice it with. So the big question is, when is a matrix diagonalizable? So someone raise your hand. Seth? Nice. Yeah. So we're only talking about score matrices here. So we're n by n. So there have to be n linearly independent eigenvectors. The way we test that is to make sure that the algebraic multiplicity is the same as the geometric multiplicity for any eigenvalue. Okay. If that's the same, then we get our n. There is a special case where you don't ever have to check your geometric multiplicity, because the geometric multiplicity is always at least 1, and the algebraic multiplicity is always at least 1, right? Because the algebraic multiplicity, you found one, it's 1, right? But so if you have matrices that have unique eigenvalues, so matrices with unique eigenvalues. I don't know how to spell unique. Is that right? They are always diagonalizable. Okay? Matrices with unique eigenvalues are always diagonalizable, because the smallest the geometric multiplicity can be is 1. And so if they're all unique, the algebraic multiplicity is 1 for each of those, and the geometric multiplicity has to be 1 for all those. So it's diagonalizable. You only have non-diagonalizability issues if you have an algebraic multiplicity of 2 or more, or at least 1 eigenvector. Yes? Yeah, so algebraic multiplicity is the number of factors it's in the characteristic polynomial. So like lambda minus 5 squared, lambda plus, we did this the other way. Well, yeah. So 5, and negative 2. So here the algebraic multiplicity here is 2. Here the algebraic multiplicity is 1. Okay, so yeah, because of this factor is squared. But when you start solving for the basis, the eigenbasis, and we'd subtract 5 off the diagonal with however many there are, and augment it with 0. We want to get x, y, z, or however many we have, equals, we're looking for the null space here, right? the number of, the dimension of the null space is the geometric multiplicity. So the number of vectors we have here is the geometric multiplicity. All right, sorry, what was that? Has to be, no, it can't ever be greater than the algebraic multiplicity. You're not going to have two factors here and end up with three eigenvectors over here. You'll have at most two, but it could, the geometric multiplicity could be less than the algebraic multiplicity. And that's when it's not going to be diagonalizable. So they have to always be equal. So for the null space of A minus lambda I. Okay. So yeah, so if you know it has unique eigenvalues, it's always diagonalizable. And that gives you a way to reason through some of the problems that are going to come up on the exam. There's always problems like that where you can help to reason through things. Okay. And you also know if they list, if you have eigenvalues that are listed more than once, you're like, you can start to know that, hey, this could possibly be non-diagonalizable. Right. Any questions about similar matrices or diagonalizability? Yes?
Wait, so by unique you mean eigenvalues? Could it be that example right there where the algebraic multiplicity is 2, or did you mean unique by each one has an algebraic
Like,
multiplicity?
yeah, like 7, 8, and a -1. This you could have a problem because the geometric multiplicity could be 2 or 1. But here, the geometric multiplicity has to be at least 1. All your algebraic multiplicities are 1, so they'll all be the same. So, okay, nice. Okay, let's get you guys working. So there's some problems on, how about the stuff you read about in preparation for today? Yes. All right. Yes. Either way. All right. So let's start going through these. Actually, before we start going through these, let's talk a little bit about orthogonal. So when you're dealing with orthogonal bases, and especially orthonormal bases, things are really nice. Like intuitively, you're thinking perpendicular, but orthogonal goes beyond that. Like some of the advantages and some of the meaning goes beyond just being perpendicular. It has to do with information and having shared information or no shared information also. So if a basis is orthogonal, then finding coordinates is easy because values of the other vectors will not change the amount you need. If we have an orthogonal basis, then I can just look at one vector at a time and see how much information in that vector is in the point that I have. And then I can capture that information, and then I can move on, and I never have to come back to that. And we can see that with projection. So here I've got this point, I've got an orthogonal basis. I can just figure out, oh, I can scale this one to this point, and that's no matter what value I have in my other vector, it doesn't matter. It doesn't even matter what the other vector is, as long as it's in the orthogonal plane or hyperplane or whatever. Like that's all I need. So we can find coordinates by just projections. So I need the coordinates would be this point in the first one, this point in the second one, or first and second. You can switch first and second there. So so we can just find them by projections. To find coordinates in this basis, then notice I have to pay attention to what one angle, the angle of one of them, to figure out how much I need of the other. Right? The angle down here, I can go, okay, from this point, I'm going to go the same angle as this one. I'm going to go that same angle over this way. And I have to pay attention to that angle to figure out where I am on the first vector. And then I have to do the same thing. I'm like, okay, well, I have to travel in this direction. And so I'm going to go down in that direction to find out how much I need of the other one. And then together, those two will be my coordinates. But orthogonality is really nice. I already know the direction, and we already have a lot of nice math that works with orthogonal vectors. Projections don't work the same over here. So if you try doing projections, so the idea is this red line right here is perpendicular to this vector, and the red line right here is perpendicular to this vector. If you tried finding coordinates just by projections, you would get, I would need this much of the first and this much of the second. And then when you add them together, you'd get to this point. And that's not the coordinate, those aren't the coordinates. So there's issues going on there. So we can find the coordinate of one basis vector, then not have to worry about it as we find coordinates of other basis vectors. This creates a nice separation where we can just focus on one and not have to worry about others. And that's because each vector has unique information that is not shared by any other vector. So if you want to have that piece of information, you only have to look at that vector, and no amount of other pieces of information or the other vectors will capture that, will change that information that you have. So for example, if you are creating a basis, if you can choose to, like if you have flexibility in what basis you're going to use, make it an orthonormal basis, okay? Or at least an orthogonal basis, but yeah, make it orthogonal. So this was the basis that they use for JPEG compression. Any 8x8 grid of pixels can be made exactly, at least in grayscale, can be made exactly from linear combinations of these. But these are orthogonal too. And that's nice because if you're trying to find how much of each you need, then you can just do the math to find out how much you need of each one. So for example, that first one that's all white, that's just your average grayscale. So you can find your average grayscale over the 64 pixels, and then you would know how much to scale that one by. It'd be somewhere between all white and all black. You'd scale it to what you need for the grayscale. And then you'd never have to change that no matter what other combinations that you'd need to get the other ones. If they weren't orthogonal, then you might find the average grayscale there, and then as you're picking other values, you might have to go back and adjust that one for what choices you made with the other ones. So that's not a very nice thing to have. And so, but orthogonal is nice because then you can just work on each one. You can find each one. You don't have to worry about the other ones. Yes, Braden.
So when you say that these are like vectors, does that mean that you make a 64-dimensional vector with just a whole bunch of grayscale values?
Yeah, you could make you could think of it as a 64-dimensional vector, one vector with 64 things. I don't know if that's actually how they work with it, but yeah, and it'd have scale values from 0 to 255, where 0 is like white and 255 is black or something, or maybe they're reversed. But yeah. Yes. So yeah, you can dot product. You could then dot product those to get 0. Yeah. So from the way I understand, there's always some way to get them into a dot product where they would get 0 from each other. Yeah. So they all have unique information, which is kind of crazy. So how they came up with it, I don't know, but pretty cool how they did. So when you're building sound in Fourier series, there is a nice basis that is orthogonal, and it's using sines or cosines where you take integer powers of x. Sine of x is orthogonal to sine of 2x, is orthogonal to sine of 3x. They're all orthogonal to sine of 4x, and those are all orthogonal. And so you can see how much of each one of those you need, and then you can start working on the other ones, and you don't ever have to go back and adjust your coefficient for the first ones. So one of the nice things about that. Like, I know you guys don't know a lot about these, like these contexts, or you don't know the details, but I'm just trying to give you a feel for what orthogonal means in practice. Yes?
I'm a little lost. How can one function be orthogonal to another?
Okay, so that question for those online is, I'm a little lost. How can one function be orthogonal to another function? So one way to think of it that would be close to the way we think about it is if you were to take a whole bunch of points that were close together. So like every 1,000th of a, you do x at 0 and then x at 1,000th and x at 2,000th and x at 3,000th and evaluate sine and sine of 2x. The sine of x, sine of 2x. And then you'd have all of those points listed for like 0 to 2 pi. And you dot product those, they would go to 0 or be super, super close. But this generalizes when you're dealing with continuous functions. This generalizes to do a kind of integral where you're integrating sine of x times sine of 2x, or any two functions. And if you integrate, in this case, 0 to 2 pi, and you get 0 out, then they're orthogonal. So you can kind of see the dot product here where you are multiplying the different values for x, like that would be matching up. And then this is doing your sum and other things. But yeah, so that is that is really nice question. But yeah, it can the generalizability, the generalization of dot products to continuous functions ends up being an integral. So, and those that go into Fourier series, you do this, except, well, we don't have to go into that. The integral will show up again in Fourier series. They often do it in terms of complex values and the exponential function instead of that. Nice question. Okay. In programming, the idea of orthogonality and programming for you computer science majors is that one part, if you don't want to start changing one part of your code and then have that mean you have to go to other places in your program and change stuff over there. That's not nice. You want to be able to change stuff here and have it just impact this. So that's the idea of programming, orthogonality and programming. Okay. We'll quickly hit these and we'll go through the problems. So I don't know why we did this, but so we have orthogonal and we have orthonormal. Orthogonal, like vectors are orthogonal if they're perpendicular to each other, if the dot product is 0. Orthonormal, like an orthonormal basis means all the vectors are perpendicular and they're unit vectors. They all have a length of 1. But for some reason, they call, when we call a matrix an orthogonal matrix, we mean orthonormal. We mean that the columns and the vectors all have unit length 1. I don't know why they just don't call them an orthonormal matrix, but when we say orthogonal matrix, you need to think orthonormal vector or an orthonormal matrix, like the rows and the columns are orthonormal to each other. So yeah, Danny? Like they create an orthonormal, they're orthogonal to each other and they're all unit vectors. So they create an orthonormal basis. The column vectors would all create an orthonormal basis for Rn, and the row vectors would all be an orthonormal basis in Rn. So for Rn. So if Q is an orthogonal matrix, then I actually just stated these. The columns of Q form an orthonormal basis. So all these are equivalent. So if you know one of these, you know all of the other ones. Okay, this is like the invertibility theorem, the fundamental theorem of invertible matrices. If you know one of those 27,000 things, no, not 27,000, but like 15 things, then you get all the other ones. So if Q is an orthogonal matrix, that's the same as knowing the columns of Q form an orthonormal basis for Rn. That's the same as knowing the rows of Q form an orthonormal basis for Rn. So you can't write down an orthonormal basis of columns and not have the rows of that. You can't write down a matrix where the columns are orthonormal and the rows are not orthonormal. It's just impossible. If you get one, you get the other one. The transformation Q times X preserves the length of X for all X. That's why the determinants for orthogonal matrices are all 1 or a -1. But if you never change the length of things, you can't scale the areas or volumes or hypervolumes by anything other than 1. It keeps them the same. The linear transformation defined by Q preserves angles and dot products for all vectors in Rn. Yeah, so the transformation of an orthogonal matrix, it keeps things the same size and shape. You're basically just moving them around. So everything stays the same size and shape. It might be reversed somehow, like with the orientation, but it's the same size and shape. Q inverse is orthogonal, and Q transpose times Q is the identity matrix, and that means Q transpose is the inverse of Q. So some of you on number 3, to find the inverse, we're augmenting things, and you were augmented it with 1 0 0 0 1 0 0 0 1. That is the process that we go through to find an orthogonal, to find the inverse matrix, and then you row it as this side, so it looks like the identity, and then what you have here is that. But you don't have to do that. You just take the transpose. If it's an orthogonal basis, you just take the transpose, and that's the inverse matrix. So that's one of the things that make it really, really nice. So, all right, so let's talk about one. So how do we show that this is an orthonormal basis? Well, you have to show that they're orthogonal. You have to show that they are length 1. So you can do dot products to show that they are all orthogonal to each other. We didn't write out the computations here, but you can do the computations. You get 0 every time. But you also have to show that when you dot product with themselves, they get 1. The length needs to be 1. Now, dot product is not the same as length, right? Really, the length would be b1 dot b1 square rooted. But since we got 1, it doesn't matter if you square rooted or not. So the dot products are 1 in each of these, so the lengths are all 1. So it's orthonormal. Okay. Questions about this?
Yeah, one other thing. I saw on the previous slide, it said that it preserved angles for the vectors. But like if it rotates the vectors around or if it spins them, doesn't that change the angle they have with the x-axis or whatever it is?
So for those that were online, the question was, wouldn't a rotation change the angles that a vector had with the x-axis? So it doesn't preserve angles. What it means is, if I have 2 vectors here, and then after I transform those 2 vectors, that the angles will still be the same. So it's not the angle to the axis, the axes. It's 2 angles with respect. It's 2 vectors with respect to each other after they're transformed. Any 2 vectors you pick at the beginning, you transform them, they'll have the same angle. So, yeah, nice question. Okay. Other questions here? Yes, Braden?
Could the transformation of every orthogonal matrix be described as a combination of reflections and rotations?
So that question was, can it always be described as a combination of reflections and rotations? Actually, you only need reflections. You only need combinations of reflections. A rotation is actually just 2 reflections. So you can simplify it all to reflections. So it might not be easiest to think about in terms of reflections, but yeah, turns out reflections are your building blocks of isometries, of transformations that can be done with an orthogonal matrix. So nice. Is this number 2? Okay, so find the coordinates of 2 and negative 2, 5. So you could, and some of you started to do this, which is fine. What's the process we know how to do with this is, let's write down a system. I need to know, here, I'll do it this way. I need to know, what do I multiply by, that's a positive, this, and what do I know multiply by the next vector? And what do I multiply by the last vector, so that together they become 2, negative 2, and 5. Okay, the A, B, and C are my new coordinates. That's what I'm looking for. Well, this we can rewrite as a system where 2 and negative 2 and 5, and here I have 1 square root of 2 minus 1 square root of 2, 0, 0, 1. So here, I can write it this way, I can row reduce, and I can solve for my A, B's, and C's. We can do this. But there's a much easier way with orthogonal matrices. Okay, so how do we do this? Well, we just have to look at the projection onto each of X, Y, and Z. So if you think about, if we've got orthogonal matrices and I have a point, then each of these coordinates I can get just by reflecting or by projecting. I don't know if that looks right or not, but the idea is that I can project onto each one of those axes, and that's going to be my coordinate, and I don't have to worry about the other ones. That's what we talked about, the idea of being orthogonal. Each one of these has unique information, and so no matter what I have with the other ones, it doesn't capture any of this information. So I can just capture the information in one and go from there. And we can just do this with projection. And the projection, remember the projection formula back from 1.2 is this, but we're projecting onto a unit vector. So V just has a length of 1. So this dot product is just going to be 1. So we just have to do U dot V. That is going to be the coordinate for each of these. So that's what this term says. If I have an orthonormal basis, then to find the coordinates of W, I just take W dot Q1. That's going to be my first coordinate, the coordinate of Q1. And W dot Q2, that's for Q2. And it's really just the projection here formula, but the denominator is 1. So that's what this student did here. Oh, to find the first coordinate, well, I'm just dotting the first column with 2, -2, 5. You end up with 0. Then the second column with 2, -2, 5, -4 square root of 2. And then the third one, 5. So the coordinates are 0, -4 the square root of 2, and 5. So really nice. Okay, questions of that? Okay, what was the question for? What's the determinant of A? Well, you've only got 2 choices. It's only going to be, it's got to be 1 or a -1. Okay, if the transformation doesn't change the size or shape, then the area or volume or hypervolume, whatever dimension you're in, can't change. So it could change orientation. The shape could change orientation, so it could be -1. In this case, 5, if you're able to figure out 5, which is hard, I wouldn't expect all of you to figure this out. Those square roots of 2s should indicate, hey, those look like sines and cosine values. So it ends up being a rotation of 45 degrees around the z-axis. So you've got z sticking up, and then you can rotate 45 degrees. I think it's counterclockwise. So, so since that rotation doesn't change the orientation, then the determinant would be 1. So, so that's number 4. I mean, you can go ahead and figure it and compute it if you want, but the idea is to think about it in terms of what the transformation is. We already talked about 5. And without calculating, what are the eigenvalues of A? So this is kind of tricky, but take a minute, talk to your neighbor. Now that we know that the transformation is rotating 45 degrees with the z-axis as your rotational axis, what would the eigenvalues of A be? And also, what are the eigenvectors? So. All right, any guesses? Hey, let's start with an eigenvector. Can someone tell me one eigenvector? There's one direction that doesn't change. Okay, yeah, the z. So 0, 0, 1, we can pick as an eigenvector. Anything on the z axis would be an eigenvector. What is the eigenvalue associated with that eigenvector? It's 1. because it doesn't change. It didn't reverse your directions, it just stays there. Because if you're rotating around it, then it doesn't change. So are there any other eigenvectors? There are no real eigenvectors in this case. So we rotate, and so nothing in the xy plane can stay on itself. The vector can't stay on its own span. So they end up being complex, and the eigenvalues end up being complex. So I think we mentioned in class before that when you're dealing with rotations, you can end up with complex. You usually do end up with complex eigenvalues. So you don't have to worry about finding complex eigenvalues in this class, where we only focus on real eigenvalues. But a lot of you, especially those in engineering, you'll have systems where you'll get eigenvalues, complex eigenvalues in your matrix, and that means that there's some rotation or some cycling going on, and you translate your complex eigenvalues into trigonometric eigenvalues, trig functions to make them easier to work with. All right, have a great day. Study hard for that exam. Yeah.